Hello everyone. In today's lesson, we're going to cover section 5.2 on finding probabilities for the normal distribution using the standard normal probability distribution. So if we have some random variable x that's normally distributed with a mean of mu and a standard deviation of sigma, then the random variable z is given by z equals x minus mu over sigma. And this is called the z transformation. And what it's telling is that we have some normal distribution which is centered on mu. And we have some data point that we want to know what is the probability to the left, to the right, or between two values. So let's say that we have some value that's right here. This is our x. This top part looks at what is the distance between x and mu. And then it uses the sigma to translate this and scale it to what is called the standard normal. So the standard normal is just a normal distribution with a mean of 0 and a standard deviation of 1. So what's happening is we're looking at where is our data point in relation to the center of our normal distribution, which is a normal distribution centered on mean, mu, and standard deviation sigma. And then we are translating it and getting a z value on the standard normal probability distribution from our normal distribution. Now, you might wonder, why are we doing this? And it's because technically there's an infinite number of possible normal distributions based on different means and standard deviations. So what we're going to do is we're actually going to use this to translate to one single probability distribution, which will then allow us to compare between different normal distributions, but also it gives us an easy way to calculate probabilities on the normal distribution without having to do the integration that we talked about in the last section. So the probability that z will equal a certain number will always be 0. We talked about this last time. For example, if I asked what is the probability that x equals some number, let's say 20. It doesn't matter what the number is, it is going to be equal to 0 because the probability out of the infinite number of different possible values that we find that single value is infinitesimally small. It's equal to 0. So generally, we're going to have our probabilities in terms of either the probability that x is less than or equal to some value. I'm going to call it a. For some number a, we'll have probability that x is greater than a, or we'll have that probability of x between a and b. So two different values. And to kind of draw what this would look like, the first one, we're going to have the probability, let's say that a is over here. We're looking at what is the probability to the left of this a value. The second one, we'll use the same a for this, would say what is the probability above that a value. And then the third one will be what is the probability that if we have some a and some b, what is the probability between those two values? Let's talk about what this actually looks like when we do our z transformation. So if we're on a normal distribution, which is centered at some point mu and has a standard deviation of sigma. So this is normal with mu and sigma. If we had some value to the left and we do our transformation, right? So this would go transform into our standard normal, which is a normal distribution centered at 0 with a standard deviation of 1. When we are to the left of the mean mu, when we translate to the standard normal, we will be left of 0, right? So let's call this A1. So A1 will translate, it's on the left of the mean mu. Mean mu will end up being equal to 0. This is because based on our z transformation, we had z equals x minus mu over sigma. Well, if my x value is mu, this is just going to become mu minus mu over sigma, which is 0 over sigma equals 0. So that mu is the center point of your normal distribution. When I translate it to the standard normal, it's the center point of that standard normal. So anything to the left of mu will be to the left of 0. Anything that is to the right of mu, we'll call this A2, will end up to the right of 0, meaning that it is negative if it's on the left. So we'll have a negative value if we're on the left, and we'll have a positive value if we're on the right. Now, one other thing I want to mention while we're doing this is you'll notice that sometimes I'm going to be using things like greater than or equal to interchangeably. This is because the equals to doesn't have any impact on the continuous probability distribution. So let me clean this up and I'll show you what I'm talking about. So if we compare our discrete case to our continuous case. For discrete, if I said something like, what is the probability that x is less than 6? We talked about this, that in the discrete case, that if I have some discrete intervals, let's say that this one is 6, and I said everything to the left of 6. Well, that doesn't include 6, and there's nothing in between 6 and 5, so it's the same thing as saying everything to the left of 5 and including 5. So this would be the probability x is less than or equal to 5. For the continuous case, if I had the probability that x is less than 6, this would look something like this, right? We got 2, 3, 4, 5, 6. Let's say that 6 is this one. So it's going to be everything to the left of 6. Well, for a continuous probability distribution, this part right here is not empty. So it ends up being the same point. So this means it's going to be equal to the probability that x is less than or equal to 6. And this is because, as we talked about, the probability that x equals 6 is just equal to 0. So therefore, it doesn't actually change anything. So similarly, with discrete probability distribution, if I had probability that x is greater than 6, this would be the probability that x is greater than or equal to 7. Whereas with continuous, the probability that x is greater than 6 would be equal to the probability that x is greater than or equal to 6. So there will be times in this section where you will see that I'll add or subtract the equals to kind of keep things consistent. For example, if I have something that is less than 6 and I take the complement of that would be everything that is greater than or equal to 6, since 6 was not included in the original statement. But for calculations, it doesn't actually have any impact on your calculations when you're doing a continuous probability distribution. Let's talk about now how we can do transformations to get our probabilities in the form that we can use based on the table that we're going to be using for this course. Now, whenever I'm looking for a probability, and we'll talk about how to actually use the tables later, we're going to get in terms of our standard normal, which again is centered around 0 with a standard deviation of 1, and the table that I'm going to supply you with is going to be for a positive value, so that is to the right of 0, and finding the probability to the left. Now, there exist tables for any situation. So for example, a positive value to the left, there you can find a table for that. Positive value to the right, you can find a table for that. Negative value to the left, you can use a table. Negative value to the right, you can find a table for that. The thing is, though, is that I'm going to specifically be focusing on this style of table because, one, it's what I'll supply to you for the class, but also it's because it's useful to understand these transformations so you can use any table that you have to get it in the form that you can use. The other thing is, when you're doing your assignments, things like that, even though you could find this stuff with a calculator, you're likely to get problems wrong because when we're using this table, we're using an approximation of the actual probability because we're not integrating between any values to the left of some value or to the right of some value. We are using a table of values that have been calculated for specific z values. Because remember, when we're on the standard normal, this will be our z value. And the thing is, not only is it an approximate because, for example, if you have a z value of 1.46389, your calculator or computer might be able to do this. But our table will always be in terms of 2 decimal places, meaning right there you're already going to be having some approximation by not including the rest of your z value. The other reason is because our values are rounded. On the table, all of the probabilities that are given will be in terms of 4 decimal places. So if you have a calculator or something like that, and you want, first of all, you already dropped off this part, and it's rounded to 4 decimal places, you might be off due to rounding. So we're just going to keep it consistent by focusing on using this table. Now, if you take later statistics courses where you're going to use integration, you can actually get more precise answers. Now, to get things in the form that we're going to be able to use for this table, we are going to look at a couple different cases to transform and get it into the form that we actually want, which I'll leave this up here to kind of show what the form is that we want. We want a positive value, and we want it going to the left. So the first example would be if we have something in the form of probability is less than, let's keep it in terms of z. Probability of z is less than some positive a value. Well, in this case, this a value is already positive, so we're good in that regard, and it's looking to the left, because less than or equal to is to the left. In this case, you can just look it up in your table. Now, let's say that we were looking to the right. So this would be the probability that z is greater than some positive a value. Or it could be greater than or equal to that positive a value. Well, we do have that it's in terms of positive, so that part is good. But if we were to draw out what this looks like, we have our standard normal, centered around 0. We have a positive a value, which means that it's to the right, and we're looking at the probability to the right. But like I said, our table is specifically for positive values looking to the left. So what we're going to do is we're going to use the fact that we know that whatever was not included in this probability to the right is the complement of that probability. And we know that the probability of an event plus the probability of its complement must be 1. And this is because they're partitioned, right? If anything is included in A, that means whatever is in not A would be everything else. So what we're going to do is we're going to use the complement, and this is going to be equivalent to taking the entire probability distribution, subtracting out everything that is to the left of this a value, which we can look up on the table because a is positive and we're looking to the left. So we take the entire distribution, we subtract off everything to the left of a, we'll be left with the probability to the right of a. So this is going to be 1 minus the probability that z is less than positive a. And now if we look at this probability, we have a positive a, and we have it looking to the left, meaning that we can look this probability up in our table. So now at this stage, we can look it up. And whatever value we get for this, we just subtract from 1, and that'll be our actual probability we're looking for. The next case is, what if we have the probability that z is greater than a negative a value? So if I were to draw this normal distribution, this would be a standard normal, where I have a negative a value, and I'm looking at everything to the right. Well, first things first, we look at, is our a positive or negative? Well, here it's negative, and we said that it needed to be positive. So what we're going to do is we're going to use symmetry, and we're going to basically just make a mirror image and flip along the axis, the middle of this normal distribution, to change this to the equivalent, which is everything to the left of positive a. So I just took this distribution and I flipped it, create a mirror image, and it'll be the same probability. So this is using symmetry. So this means that this would be the same thing as saying, what is the probability that z is less than, because it's to the left, of a positive a? Which in this case, a is positive. We're looking to the left. So we can look this up in our table. And then the last case we'll look at is, what if I have the probability that z is less than a negative a value? Well, in this case, it's going to be the same idea. I'm going to draw the pictures over here just to make sure that they're still in frame. So if I have a standard normal probability distribution, and I have a negative A, and I am looking to the left, well, first of all, A is negative. So I'm going to use symmetry to make it positive. So this is going to be equivalent to everything to the right of positive A. Now in this case, our A is positive, but we're looking to the right. And we said that we needed to look to the left. So much like we did for this second case, we're then going to, in this first one, we use symmetry. Then what we're going to do is we're going to use our complement. So we're going to take everything in the standard normal distribution. We'll subtract off everything to the left of A on our standard normal distribution. We'll be left with whatever is to the right of A in our standard normal distribution, which by symmetry is the same as everything to the left of negative A. So this is going to be 1 minus the probability that Z is less than a positive A. And in this case, we can now look it up in the table because A is positive and it is looking to the left. I said that there are 4 cases, but there's actually a 5th case. And this is because we mentioned previously that we can take the probability less than or equal to some value, whether it be positive or negative. That's 2 of the cases. We could find the probability that something greater than or equal to some positive or negative value. That's 2 more cases. But we also need to take into account, what if our Z value is between 2 values? Now, I'm actually going to kind of show that this works for any case of this situation. So we could have, for example, a negative A and a positive B, and we're looking at the probability between those 2 values. We could have a negative A and a negative B, and we're looking at between those 2 values. Or we could have the case where both A and B are positive. Now, how do we actually find this? What we're going to be doing is we're going to be using the difference formula, right? So think about whenever you're trying to find the difference between 2 values in any other math topic. Let's say you have 2 values here, x1, y1, and x2, y2. And we wanted to find what is the distance between those 2 points. How would you do it? Well, you do rise over run, right? So you check the change in y over the change in x, which is just going to be y2 minus y1 over x2 minus x1. Now you might wonder, why is it y2 minus y1 and x2 minus x1? And it's because if you were to think of this being on a Cartesian plane, if I wanted to know how far I've moved in the x direction, what I'm doing is I'm saying, okay, how far have I moved from x2 to 0? And then I'm going to find what is the distance from x1 to 0, and I'm going to subtract that off. And I'll be left with what's between them. Same thing with my y's. If I find the distance from y2 to 0, subtract off the distance from y1 to 0, I will be left with the distance between y's. We're going to use the same principle here. We are going to be looking at the probability to the left of the bigger number minus to the left of the smaller number. And then from there, in each case, we actually will then just have to do our other 4 manipulations to get it in the form that we want. So if you ever have the probability that Z is between 2 values A and B, it will be equal to the probability that Z is less than your bigger number, right? So less than B, minus the probability that Z is less than A. And this is the part that sometimes confuses people, because if you look at the original probability, it's the probability z is greater than a, but we switched it to less than. And this is because when you're actually finding this, what you're looking for is you are looking for all of the values that are less than b and all of the values that are greater than a, and it's whatever the intersection is. It's what they both share. But the way we're actually finding it is we're saying all the values to the left of b and subtracting off all the values to the left of a to get that same interval. So now that we have this, let's actually show how we would find it for these three cases. I'm going to start with the easiest case first, which is when both a and b are positive. And this is because there's really nothing to do on this one. You just use this formula here. So you have the probability that z is less than b, which is positive, minus probability z is less than a. Because b is positive and a is positive, and they're both looking to the left, you can just look this one up directly in your table. So there's nothing to do that needs to be done to transform it if a and b are both positive. Now let's look at this case. Probability that a is between, or z is between negative a and positive b. So if we did that, I'm just going to put a negative in front of a, even though it's really just a as the label. The negative is just to help you keep track of the fact that it's negative. So if we had the probability that negative a is less than z is less than b, this would be the probability that z is less than b minus the probability z is less than negative a. This probability z is less than b, I can look this up in my table, right? Because b is positive and it's looking to the left. The second part though, a is negative. So first thing I need to do is I need to use symmetry to flip it to a positive, right? Because if I looked at this, this is what I'm looking at so far, is that I'm just going to focus on this part right here. If I have my standard normal centered at 0 and I have negative a, I'm looking to the left of negative a. So I'm going to use symmetry to look at everything to the right of positive a. So this is then going to become the probability z is less than b minus, and then what is this? This is positive a, and we're looking to the right. So probability z is greater than positive a. But again, I can't look this up in my table. So what I'm going to now do is I'm going to use the complement, and this is going to become everything minus everything to the left of positive a. And that will leave me the probability that is equivalent to everything to the left of negative a. So this is going to be the probability z is less than b minus 1 minus the probability z is less than positive a. And now, a is positive, it's looking to the left. B is positive, it's looking to the left. These are the final form of what I need to do. I can look this up in my table, I can look this up in my table. The last case, which is the most complicated, is when a and b are both negative. So if I have the probability of negative a less than z less than negative b, this will be the probability z is less than negative b minus the probability z is less than negative a. And then just like before, when I have the probability that z is less than a negative, this is going to end up being, using symmetry and then the complement rule, this is going to be 1 minus the probability z is less than positive b minus 1 minus the probability z is less than positive a. So at this case, I can look this up in my table. I can look this up in my table. I subtract each of them from 1, and then I take this value, subtract this value, and I will get my final probability. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.